Hi, welcome to our video for 10.1. Oops, now we can start. Hi, welcome to our video for 10.1. Today we're going to be talking about a little bit about probabilities and how to represent them. And the title of our section is Sample Spaces and Probabilities. But before we get started, I wanted to introduce you to this term, red herring. I don't know if you're familiar with it or not, but basically the definition I wanted to talk about is when you're talking about a clue, or at least it feels like it's a clue, but it actually is intended to mislead you. And so I feel like that's going to show up today in our problems. So let's get started. So the first thing I wanted to talk about, or to kind of work through an example of, is when they ask you to find a sample space. So we're looking through example 1, and they say you flip a coin and you roll a die, a 6-sided die. So you're doing two different things, and they ask you how many possible outcomes are in the sample space and list the possible outcomes. Now they're using this word outcome. So an outcome really, well, let's make sure we have this defined. An outcome is really just the result of an experiment. And so for us in this problem, it may not sound like a science experiment, but the experiment is that we're flipping a coin and rolling a die. So how many possible outcomes are there? Well, let's list them first and then we'll know. So the first outcome I can think of is that we're going to flip and we're going to get a head, but then we're going to roll the die and we're going to get the number 1. Now we could have just as easily flipped and got a tail and also got the number 1. And so what we do is we start to realize, and this is kind of painful to think this through, but we start to realize we could write all of these out. So we could get a head and then get the number 2. We could also get a tail and then get the number 2. And so the fastest way to do this is to really pick up a shorthand to be able to list all of these possible outcomes. So how could we list these a little bit faster? Well, we're just going to shorten it up and say, well, we could get a head, or we could get a 3. We could get a tail, or we could get a 3. We could get a head and we could get a 4. We could get a tail and a 4, a head with a 5, a tail with a 5, a head with a 6, or a tail with a 6. So what are we looking at? This entire thing that I wrote out, that is called our sample space. And so we have written out all of our possible outcomes. And well, how many are there? There's 12, obviously. 12 possible outcomes. Okay, so we're starting to get a little bit familiar with the language of outcomes. We're also getting familiar with this language of sample space, and that's what this entire thing is. This collection of all 12 of these things is the sample space. Okay, let's keep moving and take a look at a different example. Oh, sorry, I think actually we're gonna try these. It's a good place for you to stop and pause. If you want to continue to watch, feel free. But it says find the number of possible outcomes in the sample space and then list the possible outcomes. So in this first problem, it's sort of a friendly problem. You're only flipping 2 coins. So what are the possible outcomes? Well, you could get a head followed by another head. You could get a head followed by a tail. You could get a tail followed by a head, and you could get a tail followed by a tail. So those are all of the possible outcomes. And again, we're kind of highlighting that word outcome. Those are all the possible outcomes. But if they want to just know the number, there are 4 different outcomes. And again, I think that we could probably figure that out if we thought about how to think about the total number of outcomes for the first coin, which is 2, and the total number of outcomes for the second coin, which would be 2, and of course 2 times 2 is 4. But we'll talk a little bit more about that, how to do that mathematically more later. All right, so for problem number 2, it's going to be a little bit more of a involved experiment. We're flipping 2 coins and rolling a 6-sided die. So the experiment involves flipping 2 different coins and then also rolling a die. So we could get a head followed by a head followed by the number 1. And we could go head, head, 2, head, head, 3. And this is going to be painful, so just bear with me. We are having to write out every single one of these options. Now, of course, with our flipping of the coins, we could have went head, tail, and then followed by the number 1. And so the best piece of advice I can give you when you're being asked to write out your possible outcomes is to do them in a way that you are making a pattern. That way you don't miss some or you don't forget some. Just basically, you're not just writing them down in a random kind of hodgepodge way. So now I'm thinking about getting a tail first and then followed by a head, tail first and then followed by a head, and then the number 2. So tail, head 3, tail, head 4, tail, head 5, tail, head 6. And then, of course, don't forget, we could have gotten tails both times. So this is, again, this is a little bit of a painful process because of how tedious it is. But what we're going to see here at the end is that we have 24 different outcomes. And the reason why we have 24 different outcomes is that our different scenarios have different possibilities. When we flip a coin the first time, we have 2 different possibilities. When we flip a coin the second time, we again have 2 different possibilities. But when we roll a die, we have 6 different outcomes we could get. When we multiply these all out, well, that is the total number of different outcomes that we could get. So here are the number of different outcomes, and this, as we wrote out, is the entire sample space, or we wrote out all of the outcomes. Okay, let's keep moving then. So one definition that we really want to pay attention to is this definition that is called theoretical probability, and it's the probability that something can happen, or it's the chance that something that can happen. And what we are always going to be looking at is we're going to be looking at numbers from 0 to 1, where you could have the probability be 0, you could also have the probability be 1. And the main thing I wanted to highlight in this is that your probabilities can be written out as decimals, they can be written out as fractions, or as percents. And so you can see that they've written those out in all 3 different formats. And so obviously if the probability of something is 0, it's not happening, it's impossible. And obviously if the probability is 1 or 100%, it is absolutely a certainty that it's going to happen. So let's keep moving then. We'll kind of apply these ideas to different problems, but just keep in mind the theoretical probability is the likelihood or the chance that the event will occur in theory. Okay? So taking a look at this, we're saying, all right, what are the ways that we can find the probability of a complement? Well, let's make sure we understand when we're talking about a compliment here, we're not talking about being nice to someone or using kind words. We're talking about the probability of getting the opposite of that event to take place. So if somebody is asking you for the probability that the sum is not 6, well, you can do this in a couple of ways. Let me show you the first way that we can do this, and what I would say is in big fat letters, do not do this. You could go through and you could find the probability of not getting the sum equal to 6, and you could go through and you could highlight, and I'm going to use blue here, you could highlight all the sums that aren't 6. Well, 2 isn't 6, and 3 isn't 6, and 4 isn't 6, and 5. Well, that one is 6, 7, 3, 4, 5, 7, 8, 4, 5, 7, 8, 9. Holy moly, there's a lot of these that are not 6, and this is taking forever. And most of us, when we're doing, pretty much anything, we don't want to take this much time to figure out the problem, figure out the answer to a problem. Now, again, emphasis on the fact that this is not how you should do these problems, but we now go through and count them all up. There are 5 in this, 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 and all 6 of those do not add up to 6. Well, how many in total is that? Let's see, 5 and 10, 10 is 20, 25, 31 different ways out of 36. That's the answer. That is the correct answer, but that was a really slow and methodical process. So let's look at a faster way to do this. Let's look at a little bit quicker way to do this, and that is by figuring out the probability of the complement. So complement is where we're saying find the probability that the sum is not 6 is equal to 1 minus the probability that the sum is 6. So again, it's kind of like finding the opposite, or the thing that it isn't. So we're pulling that away from 1. So 1 minus, so what would the probability be that the 2 die add up to 6? Well, all we have to do is we have to find all those patterns where the numbers add up to 6. So 1 and a 5 is a 6, 2 and a 4 is a 6, 3 and a 3 is a 6, a 4 and a 2, and a 1 and a 5. And how many of those are there? There are 5 of those out of 36 total. Again, when we subtract that out, we get 31 over 36. That is our probability. Now, as we said earlier, when we're doing probability problems, you can answer those problems using fractions or decimals or percentages. So another way that you could have written this out is you could say, or that's the same thing as 0.861. That's another way of writing the answer out. It's about 0.861, but another way somebody else might choose to say it is that, or it's about 86% chance that if you were to choose 2 of these dice, the sum would not be 6. And obviously there's a lot of them that add up to something that's not 6. So that's how I would show how to find the sum of complements. Now let's take a look at problem B. A little bit similar, a little bit different. What is the probability that the sum is less than or equal to 9? And we're going to try and do this using the same thinking. So what would it be the opposite of something that is less than or equal to 9? So 1 minus, what is the opposite of something being less than or equal to 9? I would say that the sum is greater than 9. And again, you can go through and count all the die in here where the sum is bigger than 9. So here we have the sum is exactly 9. Well, we're not going to use that one. So, but anything where the sum is greater than 9. So I've got a 10, I've got a 10, I've got an 11, I've got a 10, 11, and a 12. And so if I count all those up, I've got 6. So 1 minus 6 over 36, which is the same thing as 30 over 36. And that will, of course, reduce. Both of those are divisible by 6. So I've got 5 over 6 is a possible answer. But again, you want to be able to be comfortable in answering these in different formats. So that would be the fraction. You could also write it out as 0.83 repeating. Another way you could write this out as a percentage is about 83%. So the chances of you finding 2 dice where the sum is less than or equal to 9 is about 83% chance, which is, again, pretty obvious when you consider that most of the sums are less than 9. So a really good chance that that would happen. Okay, so that's us using kind of the opposite of something in order to find its probability, because sometimes it's easier to find the probability of its opposite and then just subtract that from 1. So let's look at a couple of practice problems again if you want to pause and see if you can figure these out on your own, but this is going to be pretty straightforward. So problem number 4, if I'm asking you to find the probability of a complement, and that's what this is, I'm going to highlight this up here, that's what we're asking you to do, find the probability of the complement of A. Well, again, keep in mind how we do that is we say 1 minus the probability of A. So 1 minus 0.45 is, of course, 0.55. So, and that was problem number 4. Problem number 5, they're asking you for the probability of the complement of A, but they're expressing that in a fraction, so 1 minus the probability of A. Well, 1 minus 1/4 is, of course, 3/4. Problem number 6, the probability of A complement is, of course, just 1 minus the probability of A. Well, and in this one, it's a little unique. The probability of something happening is 100%, so they're saying the probability of A is 1, so 1 minus 1 is 0. That's the probability of A complement. So the probability of that problem is 0. And then for problem number 7, what's the probability of A complement? Well, it's 1 minus the probability of A. Well, here they're saying the probability of A is pretty small, 0.03, so the probability of its complement must be pretty big, about 97% or 0.97. That would be the answer to problem number 7. Okay. Now, next vocabulary word I wanted to talk about is this idea of an experimental probability. It's a little different than theoretical probability. An experimental probability is based on repeated trials. Now, we're going to use this word trials, but think of it really as an experiment where you're conducting some type of an experiment. So this is different than theoretical. Theoretical probability is it happens in theory. It's not necessarily an action that you're doing. An experimental probability is where you count up all the number of times that you had success and you divide it by the total number of trials. That's how you find an experimental probability, and that's a little different than the theoretical probability. So let's take a look at an example problem where we're kind of looking at this and see if we can make some sense of it. So they're giving us a spinner, and there are 4 colors on this spinner, and obviously we can see that there's a yellow and a green and a red and a blue section. So, but what it's saying is that each section of the spinner shown has the same area. What does that mean? Well, each of these regions is a quarter circle. They all have the same area on the circle. And they're saying the table shows the results for 20 times that we spun. And so what I want us to think about is what would be the experimental probability. Well, if we think about the experimental probability, it is really going to use the results of our experiment. And so let's take a look at the experiment. If we're saying 5 over 20, well, that's 1/4. Okay. If we're saying 9 over 20, well, that's not something that's going to reduce, but that's a pretty good chance that we landed on green there, which I don't know about you, but I guess bet on green for that problem. For blue, obviously, it would be 3 out of 20, and for yellow, it would also be 3 out of 20. Now, let's compare that with theoretical. So what would the theoretical probability be? So the theoretical would be, what in theory would we expect happen? Well, think about why in theory we would expect it to be a 1 in 4 chance. Well, it's because each of those areas is 1 in 4. So 1 in 4, 1 in 4 for green. They all have the same theoretical probability. It's just that their experimental probability is a little different based on, of course, the experiment. Now let's go back to the story problem. It did ask us to think about something. It said, for which color is the experimental probability of that color the same as the theoretical probability? Well, it looks like we've got a 1/4 here and we've got a 1/4 here, and that's the only time that happened. So it looks like red was the big winner. Red was that color. Okay. So that question was really sort of written to see if people understood the difference between experimental and theoretical probability. All right, we've got one more example here. And this is sort of where we were talking about a red herring before, but let's read through all the words here in the story. So it says, in the United States, a survey of 2,184 adults ages 18 and over found that 1,328 of them have at least one pet. And then it says the types of pets of these adults are shown in the table. What is the probability that a pet-owning adult chosen at random has a dog? So what I'd like to do is I'd like to make a couple of highlights here. We're looking for a probability, so our answer has to be between 0 and 1, including either of those two potentials, and that we're looking for a pet-owning adult, and we're also looking at something that has to do with dogs. So obviously we're going to be using this data point up here, the 916, but the question is, where do we have data that relates to pet owning? So let's go back into the story. In the United States, a survey of 2,184 adults of ages 18 and over found that 1,320 of them, 8 of them, have at least one pet. That's the key idea. This number 2,184, as I said earlier, is a little bit of a red herring. It is just there to distract you. So if we're looking at finding this probability, then we're going to say 916 divided by 1,328. That does reduce. That is a number that can be reduced. It's not a super friendly fraction, but 229 divided by 332 would be our answer. Or we could think about writing this as a decimal, 0.69, or we could think about writing this as a percentage. About 69% of our pet-owning adults have dogs. So it's a pretty high percentage. Any of these answers would be appropriate, but that's how we would work through that one. So let's take a look at these last two problems. They do ask us to reference our examples. It says, in example 5, for which color is the experimental probability greater than the theoretical? So let's look back at our experimental and which of those fractions was actually greater than the theoretical. So our experimental of 9 over 20, 3 over 20, 3 over 20, 3 over 20, 3 over 20, those are pretty small numbers, but what is that as a percentage? 3 divided by 20 isn't a very big number. It's 0.15, And keep in mind, all of these are 0.25, so those would be smaller. The only one in which our experimental is bigger is, of course, for this color green, we have 9/20. So the answer for this problem would have, here, I'll do this just to make sure we're all on the same page, is green. Okay, in example 6, what is the probability that a pet-owning adult, again, highlight some of these keywords, the pet-owning adult chosen at random owns a fish. Well, number of people who have fish in this problem, let's take a look back at this table. There are 146 fish owners. That's a lot of fish owners. 146 divided by 1,328. And of course, you can rewrite that number. Let's see if we can reduce that. 146 divided by 1,328 is 73 over 664. That would be your answer as a fraction. If you're going to find that as a decimal, you could say, or that's about 0.1099. If you're going to express it as a percentage, you could say it's about 11%. So those are some examples to help you to think about section 10.1. Always, if you have questions,